And Eddie took a job in Singapore recently, so now I'm kind of running it on my own. But we have an event today where we're going to debut AsterixDB, which UCI's ICS department's been working on for about 3.5 years now, so it's pretty exciting. So we have pizza, we have Coors Light, a Chardonnay, and Coke outside, if you haven't got any already. And just wanted to introduce our sponsors, because they help us pay for all this stuff. And wanted to introduce PSSC Labs. So this is Eric Lesser from PSSC Labs, and he'll go ahead and introduce his company based in Lake Forest.
Thank you. Actually, it's quite interesting that we have beer and wine on a Thursday night at university towards the end of the year. I remember when I was in college, we were crazy. We'd start our weekends on Tuesday or Wednesday, and we didn't have enough money for Coors Light. We were buying Milwaukee's Best. So good for you guys that we can enjoy something nice, nice refreshing beverage. PSSC Labs is a hardware supplier for servers and Hadoop clusters. And we've been in business since 1988. All of our systems are assembled here in Southern California. We're all supported here in Southern California, and we've deployed our. Okay. And we've deployed our systems all over the world. So we've been a sponsor of Orange County Meetup Hub for since the very first event, and you know, we're happy to continue to support this community. I do want to announce that on Tuesday of this month, which is the 25th at 11 a.m. Pacific time, we're going to be doing a webinar to cover a couple of topics. Probably of most important to you guys, the topics are optimizing the cluster hardware and software configuration for Hadoop and big data analytics, and also the cost analysis of owning a Hadoop on premises versus using the cloud as a Hadoop resource. So we're going to be sending out some reminders for this, and you'll see some emails as well as posts on the meetup group. But anyhow, thanks again, and enjoy the beverages tonight.
Yeah. So in regards to the webinar, I'm going to send an email out tomorrow, a mass email, and it will give the link to where you can register for the webinar for PSSC Labs. So it's free if you're a member of Orange County Hadoop User Group. And to get on the mailing list, you just use an app, either iPhone app or an Android app, and the app is called Meetup. And then you just join the Orange County Hadoop User Group, and then once you join, you're on the mailing list, and you'll get emails telling you about future events, future webinars. So I wanted to introduce David Cooley from MapR, and he works out of Orange County. So here, you can take the mic and tell everybody a little bit about MapR.
So we're also a sponsor of Meetup, and MapR is a software company based in San Jose, and I am located down here in Newport Beach, work in Southern California generally, as well as points west or east, and theoretically west if we can ever find any business out in Hawaii, so wish me luck in that. So we are a software company. We produce a distribution of Hadoop that's really the most technologically advanced distribution of Hadoop. A lot of that new technology is in the file system, which underlies the Hadoop stack. Instead of HDFS, it's HDFS compatible, but it's totally rewritten from scratch to do a lot of things that enterprises need, give a lot of data protection and other sorts of capabilities that you can't get with HDFS. So that's basically what we do. I just wanted to mention, I have background in the university myself, and I'm curious how many folks here are graduate student or above at UCI or another university? Yeah. You guys have a look. I used to have a look too. I don't know if I still do. So anyway, glad to be here. Looking forward to learning about AsterixDB, and it sounds like really interesting technology, so looking forward to hearing. Thank you.
Thanks, David. So we're going to introduce Dr. Michael Carey now. And he was one of the driving forces to make all this happen, to bring the Orange County Hadoop User Group to UCI. So we started off in conference rooms of corporations, and then we kind of grew out of these conference rooms, needed a bigger space. So I met with Dr. Carey a few months back, and he really was enthusiastic about setting up these events and wanted to give the students something extra. So I'd like to give a round of applause for Dr. Michael Carey. So come on up. So I'm going to hand it over to you now.
All right, thanks everybody for coming. So the plan is that after tonight, within a couple months, we're going to move this group into the Bren Events Center because we're going to have that many people wanting to do big data things. So we figure we're ready here at UCI. Okay, how's that? Is that loud enough? Up higher, down lower? Higher. Start with higher here, and then we'll try higher on that. How's that? Better? Turn it up. How's that? Okay, good. All right, so thank you all for coming. This is sort of an exciting time for our group, and you can see a lot of our group is here. You look for the steel gray t-shirts. I'll talk more about those. That's our group, and so if you have questions, they'll be able to answer them for you after the talk. So I'll try to avoid all questions and defer them to the group, so you know how to find them. Just look for the t-shirt. What I'm going to be doing today is talking about this new system we've been building, and I'll sort of give you the history, kind of first of big data from our perspective, and then also the history of this particular project, sort of why we did what we did, how it relates to Hadoop, which is sort of the focus of this user group, and sort of hopefully by the end you'll understand sort of what we've been up to for the last 4 years. But today is the culmination of about 4 years of work. We're basically putting this up, and we'll show you at the end where you can find it for public consumption. So we're sort of going open source as of today. It's been open source quietly for a long time, but now it's something that we're actually saying, yes, you can try this at home, and hopefully no one will be harmed. So this is the next generation system about big data management, and a couple things you should know. So first of all, we do have these t-shirts. We don't have them for everyone, but they're these cool shirts. They have sort of the AsterixDB logo here, and they have AsterixDB on the back, and you can get one, and there's a couple ways. So you can be the person who the group thinks asks the best question, sort of by the end of the talk or at the end of the talk. And so they'll sort of get together, and you might get that t-shirt. Also, I'll tell you in a second how to tweet about this if you want. And so if you're determined to have sort of given the most tweets, not just the most, but the, sort of useful tweets, you could get a shirt. Or sort of 3 lucky people who sign up in the near future on the AsterixDB users list will get selected for t-shirts. And so you can do any of those things, or all of those things actually, to try to get one of these shirts. And clearly, these are worth getting. Right? So anyway, that's where the users list is. If you go to go.google.com, AsterixDB, you can get a link from there and join the group and start hearing about what's going on as of today with this new thing. If you want to tweet about us, because that's sort of one of the ways you can get a shirt, is AsterixDB is the hashtag to use, and so we'll be watching in the back to see how things go there. Okay, so now sort of back into the more academic mode. So this is actually more of an academic talk, so I'm going to give you the context and kind of give you the perspective, at least from somebody in an ivory tower, of kind of 2 things that have been happening in parallel, slightly time-shifted, about big data. So this will be like a history lesson times 2. One is kind of from 1970 to about the 2000 time frame, and the other is from like 95 to about now, and what's been going on and how they're coming together. And then I'll be telling you about sort of the main thing that we want to talk about tonight, which is AsterixDB, which is our next generation BDMS. And that's not actually a typo. It's a big data management system, not a DBMS, and we'll talk more about that. And then I'll also tell you about our software stack and how it's sort of different than the Hadoop stack, and why it's different and so on. And at the end, I'll try to convince you that we've got something that could be used for a lot of different kinds of use cases. We don't believe in one size fits all, but we do think one size kind of fits a bunch, and I'll try to explain that. And then we'll take your questions, and we'll actually answer them in parallel with this group. So we'll do a big map task and answer your questions. And also, if you're interested in specific areas of what we've done, we can give you sort of the right person to talk to who can tell you more about that area. And we even have 1 or 2 people who could give you a demo if you want afterwards. Okay, so why did we do what we're doing? Well, because for a long time, like I grew up in the database era, sort of embarrassed. People would be like, "What do you do?" I'm a baseball player. What do you do? I'm a musician. What do you do? I do databases, right? So it's sort of embarrassing. So at parties you'd hide in the corner, but now we do big data, and big data is on the front page of the New York Times every so often. And so actually we have been doing what it says there, working on a framework to allow construction of large-scale analytical queries on unstructured data. We have that. We're about to talk about that tonight. And so it's cool stuff, right? So we're not embarrassed anymore. So what about big data? So basically, as we all know, there's been a ton of stuff. We're all tweeting, hopefully, right now about AsterixDB and other things, and all this sort of digital exhaust is getting generated behind all of us. Status updates and check-ins, and there's all this stuff that companies are starting to realize has lots of value. There's a lot of different places in healthcare and so on where they're realizing if they look at public data, they can see trends ahead of time that sort of the real healthcare people will see a few days later, and so on. And there's also, sort of a large quantity of users now generating this data. So Facebook has, roughly 1 billion active users. Twitter has lots of users. They're all doing stuff. So the world looks like this. We have people doing stuff. That stuff is happening in sort of different ways. It's all getting amassed, or could be amassed somewhere, and is being amassed in some places, as we sort of read about in the paper, even recently. And the question is, like, where, other than that, could we store this data? How could we find a way to sort of store and make use and get value from this data? And that's a lot about what big data is trying to do. And we'll tell you kind of how we think we can help with that. And so we're sort of aiming at a sort of a web warehousing or big data warehousing kind of use case, and we'll say more about that too. Okay, so let's do history lesson number 1. So there's the database world, and some of you, how many people would say you're like a database person? Okay, so there are a few, but not so many. So the database people would tell you, we've been doing this already. What part of big data didn't you understand, right? So enterprises have been wanting to store and query historical business data forever. In the 1970s, we had megabytes of data to put somewhere, or maybe gigabytes of data we could envision being around the corner. And that sort of big has changed over time. But in the 70s, we had relational databases with SQL. In the 80s, people realized that to deal with large amounts of that stuff, you might want to use multiple computers, and so parallel databases were born. Research at University of Wisconsin generated a system called Gamma. University of Tokyo, a system called Grace, which are kind of the two sort of big initial systems. Teradata, which is located just sort of nearby here, and some of you may be affiliated with that, and others of you may have dealt with it sort of in your workplaces. It's a big parallel database system that was born in the 80s and has been doing sort of shared nothing, parallel, high-performance query processing for years. And there's been a rebirth, and so in the 2000s, you see, like in the 90s, there was a lot of sort of research related to that happening, but in the 2000s, a whole bunch of companies, Netezza, Asterdata, sort of the list there, Data Allegro actually located just about 10 or 15 minutes away from here. All these companies sort of were trying to be sort of the next Teradata, and it became clear that there was a market and a lot of interest in dealing with big data, being able to do that in a more commodity kind of way. And all these companies have been quite successful, at least to the point of being acquired by other larger companies, mostly for at least hundreds of millions of dollars, one of them for over $1 billion. And so this has sort of been a big space that's been exploding. Underneath all of this, ever since the 1980s, is the idea that you can parallelize something by sort of hash partitioning or partitioning your data across multiple computer systems that don't share anything but a network. They have their own processors, their own memory, their own disks, and you partition the data and you parallelize the computation, you send the computation to the partitions. And so this has kind of been the history of big data in the database world for doing parallel query stuff. For doing online kinds of things where you're trying to sell things on the web, sort of manage auctions at eBay, or sort of do sort of online commerce in Amazon or whatever, the OLTP applications are underneath those, generating big data, but also needing to scale. And again, shared nothing is one way that those have scaled. And so as an example, as far back as the 1980s, again, this is ancient history, Tandem had a system called Nonstop SQL that was used widely kind of in financial services and other areas to do transaction processing, again, in a shared nothing architecture. And so that's kind of the world of databases. And they ended up sort of offering us, as potential customers, a stack of software that looks like this. And so at the top, you talk to these systems through a high-level language called SQL, which a bunch of you have, I'm sure, sort of dealt with and at least heard of. So you talk in a language that says, this is what I want the system to do. Find me the employee and department information. If the employee is in the department and the department's on the 10th floor, you can write that as a SQL query and get your result back. And if there's lots of employees, that can be done in parallel on lots of computers. And so at the top, there's the SQL language, and then the software stack has a compiler that takes your request and turns it into the way that the system is going to process it, has a data flow layer that executes that sort of the query plan that has been decided for your query, and at the bottom, that is executed over a whole bunch of storage managers, running on multiple computers, each doing their piece of the task and kind of feeding the data flow. And so in this architecture, there's one storage manager per machine and a big parallel cluster, sort of tens or hundreds of computers typically in parallel database kinds of configurations. They tend to be fairly high-end machines. The upper layers are orchestrating sort of the execution of the lower layers. And in fact, a lot of those sort of 2000-era startups took an open source database and some orchestration software and created a parallel database that way using partitioning. And then at the bottom, there's the storage itself, which can be row-oriented or column-oriented if you've heard about that. But there's these three layers. storage manager per machine, the upper layers are doing orchestration, and then you have the bottom. The thing to note about this stack is it's closed. So a couple things. So one is, if you want it to be parallel, you have to pay for it. So Teradata will sell this to you. Oracle will sell you something. IBM will sell you something. All these companies have products that are based on this, and they're not necessarily cheap. And you can only talk to your data through SQL. Right? So you can ask your questions and organize your data. You have to think about how you want to design your data. You sort of design the database. You put your data in the database, and then you talk to it through SQL. And so it's kind of a closed one-way in, one-way out stack. And that's the world of parallel databases. And for those of us in the database world, it's like, what more could you possibly want? You have a great language, it runs in parallel, our job is done. Wrong, apparently. So in the systems world, kind of the distributed systems world, the web started to happen while we were sort of patting ourselves on the back about our parallel databases. And in the late 90s, companies were facing the need to index and query web data. And so there are companies that sort of tried to use database technology early on to do this, like Ink2Me. Many of you remember that company. They were sort of a pre-Google search engine company that was pretty cool. They tried using database technology and concluded they needed something like it but different, built their own. Everyone needed to do something and realized they had to build something. And so sort of leading into where we are in big data today, the most significant player was probably Google, which had sort of a few thousand Stanford PhD graduates and lots of money and needed to do something. And so they said, okay, how do we store big data? We need a big file system with big files, right? So that would be a way of having big data. And so they basically made it possible to have byte stream files, sort of the usual file system model that span thousands of machines potentially, to make that system replicate data so that if you come up to the system and you ask for your data, there should be a couple of copies of your data somewhere so that somebody will have it sort of at all times that you can talk to, so high availability through replication. And they built that as a service for storing like the web index that they were creating. The next problem you have if you can store big data is you have to write big programs to process it. And so you need to do parallel programming on these machines. And for many, many years, people have been studying how to do parallel programming, and there's lots of cool papers about it. But nobody had really figured out a way of doing it effectively, write message passing programs or try to figure out parallelism from non-parallel programs. What Google said was, we have an idea, we can steal some things from functional programming, and we can offer what we now know as the MapReduce programming model, where you think about one piece of data, right? And what would you do with one piece of data to do your task? You do a map function, which takes a piece of data and produces a key value pair. And then everything that has the same key would get routed to another task that gets to see everything with that key value and reduce it into something else. And then if you need to compute something more complicated, you could do another job that does that same thing. And so they basically said, you, Mr. User, or Ms. User, you need to think about what you would do with one piece of data and one group of data that has common keys. And all you have to do is think about that. Don't think about messages or parallelism or concurrency. Just think about sort of in a data-intensive kind of way, and we'll take care of the rest for you. So they would then apply your functions to arbitrarily large amounts of data. And so basically, you could characterize this as a parallel programming for dummies model. You don't have to understand message passing programming to write a program that runs against terabytes or even petabytes of data. The MapReduce runtime does the heavy lifting. So this is a huge thing for people who need to process large amounts of data and do it in a timely kind of way. So pretty soon everybody wanted this, right? So Yahoo said, hey, we could use that, Facebook could use that. And so the file system work and the MapReduce work, the papers were written by Google and were taken as specifications, and basically open source equivalents were born. So HDFS, the Hadoop distributed file system, which MapR now has, an alternative to the Hadoop MapReduce programming paradigm, those things became specifications from Google to the open source world, and we were given Hadoop and the yellow elephant and the distributed file system, and they're in wide use today. That's why you guys are here meeting every couple months. If you go on an annual basis up to Santa Clara, the number of people there for the Hadoop World kind of conference is like doubling every year, and so this is an exploding area. What we've seen happen, us, the community, is that MapReduce is really cool. It enables people to write Java code to process their program or their data with their little sort of data minds as opposed to thinking about parallelism. But it's a tedious way to solve problems. So pretty quickly people want to do something else. And so Yahoo said, okay, we have some ideas from declarative languages and databases. We can invent this thing called Pig, which is essentially kind of a relational algebra-oriented language that processes data in steps. And you can write those steps in a high-level way. And we'll compile those into MapReduce jobs. IBM had a language called Jackal that had a similar concept, and Hive is the other sort of famous, the big gorilla from Facebook, which is essentially SQL for parallel data compiled to Hadoop. And these things are in heavy use. These were some numbers from a while ago. Yahoo said, for their own site, they were seeing over 60% of the MapReduce jobs a couple of years ago being pig jobs. Facebook was saying, over 90% of their Hadoop jobs were actually Hive queries that had been compiled into Hadoop jobs. These numbers are probably higher today. We've been talking to a lot of different companies. We've made a visit to Netflix, and there, we have Pig and Hive, and pretty much all of our MapReduce jobs are one of those two. Pig are for the ETL kinds of or data transformation jobs. Hive are for more the query kinds of jobs. But this is pretty much now how people are using MapReduce. They write Pig programs or they write Hive queries. And there's a similar sort of story at Microsoft where they have a file system called Cosmos, runtime called Dryad, and some high-level languages called Dryad, Lake, and Scope. Scope is what sits underneath Bing and kind of powers their back end. And so this has kind of been the trend in the distributed systems world and parallel with what happened, but slightly later than in the database world. And then similarly, the big data world has sort of their equivalent of OLTP. If you want to build gaming sites or you want to deal with user profiles when users log in really quickly, you need something which is sort of quick and dynamic. And so the so-called NoSQL systems were born, or the key value stores, so where you can sort of store something by a key or get it back by a key. Here's the user ID, get me the user profile quickly, and do very simple things with records, not have to talk through SQL. And so these things are characterized as being fast, highly scalable, and highly available for storing vast amounts of data if what you want to do is get and put, essentially, based on a key value. And again, sort of Google invented one called Bigtable. Amazon invented a proprietary one called Dynamo, which they were using kind of inside their systems. And then sort of open source versions of those came out of the papers that were published. The Bigtable spec gave us HBase, which runs in the Hadoop world. The Dynamo spec gave us Cassandra, and so on. And so again, in the open source world, there's a software stack. And so this is kind of an artist's conception of the open source, the stack that sort of this meetup group is about, which is the open source Hadoop stack. And so at the bottom is HDFS, the Hadoop distributed file system, where the idea is the world's largest files can be stored here. Right? So there's giant byte sequence files at the bottom. If you're writing an analytical program, kind of using the MapReduce paradigm, you're writing your map functions and reduce functions and creating jobs and executing. That runs on the blue layer, the Hadoop MapReduce layer. And basically that takes and runs your map job against all the data, then reshuffles the data sort of based on keys and sorts the data based on keys, feeds that into your reduce tasks, and those things get to process the groups that they've been promised to see. And then you may have a job that does a sequence of those. And so that's happening at the blue layer if you're kind of rolling up your sleeves or already wearing short sleeves like I am, and you want to write kind of MapReduce jobs. If you want to do key value stuff, HBase sits on top of the Hadoop distributed file system and gives you sort of record level get and put. And then at the high end, if you're more interested in writing sort of quickly and getting your results quickly in terms of working in a very productive high level, you're writing Hive queries and talking HiveQL, or you're dealing with the Pig system from Yahoo and Hortonworks and doing Pig Latin, or maybe using the Jackal facility and IBM's sort of big data story. And so you may be talking at a high level. What's different about this picture is a couple things. So first of all, it's not a closed thing where you can only talk to it through HiveQL. It's open. So you can use multiple languages to talk to the same data. You can run a MapReduce job in the middle if you need to do that because you're doing something complicated. You can even just talk sort of key value get and put operations, or you can do high-level language. And so it's sort of an open stack. And if you don't like what's there, it's open source and you can get it and you can muck around with it and improve it sort of in your own company. And so we've seen, like you see for Linux, you see sort of different lines of Hadoop and different versions and so on. And so this is sort of the open source version. And so now the database world is sort of paying attention, looking at this going, this is pretty cool. Everybody loves big data. They're talking about it at parties. Look at this architecture. What do we make of this? And that's kind of the database answer. It's like, wait a second. Who said that's the right way of building a system? We actually figured out how to build these systems. The fact that we have this big byte sequences is not necessarily the best underpinnings for a high-level language. We don't necessarily want to have to sort of compile SQL down to map and reduce. Why do we have this architecture? The answer is because this is how it grew up. So it's sort of an accidental architecture. It's very effective because it's there. People have big clusters. But if you were to sort of know from the outset that you were going to do Pig or you're going to do Hive, you might have a different architecture. And so that sort of got us thinking about, like, what should the next generation architecture for big data management look like? One other thing about existing solutions, and sort of this is at the current point in time, and then I'll tell you more about AsterixDB. And so if you're sort of a web company and you're trying to do something, you start out small and you put your data in MySQL because you like the price, it's free. And then you realize, maybe you're not getting the performance on your website, and so you put some Memcache in front of that. And then your business guys start asking questions about what's going on. And so maybe you have to roll in Hadoop. And maybe, at some point you decide you'll try one of these NoSQL things. And then pretty soon your programmers are saying, I just want to ask a query. Why do I have to write MapReduce? And so in comes some combination of Pig and Hive, probably both. And then you have to figure out kind of how you move data among all of these things. Right? So there's the bubblegum and mailing wire that kind of puts all this stuff together. That seems to be what a lot of the big shops look like today. So this was kind of our take on what was happening. I actually gave this, or a version of this talk, about a year or two ago, sort of behind someone else who consults in this area. He had a very similar slide, except he was from Europe and he had duct tape and chicken wire. So after the talk, he came up and said, the real problem is there's no standards. Is it mailing wire or chicken wire, and is it bubblegum or duct tape? If we could solve that, we'd be done. But seriously, this is what people are sort of doing and seeing. We also had a visit from people in our med school about 2 weeks ago who were doing some work with Hadoop. And basically they're gluing together sort of MongoDB and Hadoop, and they're using multiple languages. And he went, it's pretty interesting that you chose sort of these pictures because this is what we're doing. And so anyway, that's something that you see right now. And the question is, do we need that many systems and have to solve that many data integration problems and data migration and data movement problems? And so we said, okay, let's think about, because we're at a university, we get to stop and think, and we don't have to ship a product, except tonight we're trying to, kind of. Let's think about what would happen if we were to build the next generation system. And so what we did was to say, there's sort of like 3 areas that we should be drawing technology from, ideas from, and trying to figure out like how to create a best of thing by putting them together. And so at the bottom left is parallel databases. So again, we just went through the history. There's a lot of knowledge there about how to process big data very efficiently. What are the right algorithms for doing parallel stuff? How do you avoid having to sort data all the time? What are the greatest hash-based methods for doing things fast? A lot of good ideas from there that can be brought to bear on the world that Hadoop has. On the right-hand side, the Hadoop world, sort of the data-intensive computing, or big data as it's called today world, has a lot of sort of value also, and I'll talk about that on the next slide, where the parallel database sort of community missed the boat on some things that would be good features for their systems. And then finally, data is not so structured necessarily anymore. And so a lot of companies have like Teradata for their traditional relational stuff, for their business data, but then they're using something else or some combination of something else's for dealing with sort of the digital exhaust that they want to analyze and get value from. And so there's semi-structured data management. There's actually been work done in academia on that since about 2000. And so there's ideas to be drawn on there about how to think about semi-structured data. And we said, okay, let's actually think about, if we had a big cluster, taking ideas from all 3 of them and creating a system that sort of is a best of or a learns from kind of system. And that's what AsterixDB is about. And so the triangle is kind of our drawing from these 3 different areas. And so the project, what have we been doing? So basically trying to build this new, what we're now calling the BDMS, because the term big data was coined a couple years ago while we were in flight. The idea is to run it on the same kinds of clusters that you see for Hadoop, on Hadoop-style clusters, to handle really massive quantities of semi-structured data, and I'll tell you what we mean by that. To have it be openly layered, because people seem to like the idea of being able to choose. Do I always have to use that language, or can I come in and write a program against that data with some other technology that I like? And so we want this to be openly layered and to interoperate with other kinds of data. We'll talk about that. And then the goal was to share it with the community, and that's what's happening right now. We've also been doing research and have a research agenda going forward, and this is going to become our